In this lesson, we're going to go over the introduction to graphing rational functions, and we're going to identify all of the key features that we need in order to graph rational functions. So the first thing that we want to do is to think about the two different types of functions we can have. There's a continuous function and a discontinuous function. A continuous function is just that, it's continuous, meaning that if we were to draw this graph, we can draw it without picking our pen off the paper. With a discontinuous function, we can't draw it continuously. We have a jump or break in the graph. So we can see here it's continuous at this piece, but then we have to pick our pencil off the paper, draw the next piece, pick our pencil off the paper, draw the next piece. So we're going to talk about when we have a discontinuous function. There are things called points of discontinuity. So any value that makes the denominator 0 is a point of discontinuity, and those are our domain restrictions. So throughout this entire unit, we've been simplifying these rational expressions, and we've been finding the domain restrictions. And the domain restrictions are going to be what makes this function discontinuous. Domain, remember, are all of the x values that we can have for a particular function. And in this case, when we have a rational function, the domain will be all real numbers except for the domain restrictions. So we know how to find the domain restrictions. We said that x cannot equal whatever and whatever. So our domain would be all real numbers except that x can't equal whatever or whatever. Okay, there are two main types of discontinuity. The first type is removable, and that means that a factor can be canceled from the numerator and the denominator. When that happens, it results in a hole on the graph, and these holes should be written as a point, and you can have more than one. The other type of discontinuity is non-removable, and that means that you cannot cancel out any factors, and that results in a vertical asymptote on the graph, which should be written as x equals a number. Now, an asymptote, we've talked about those with exponential and log functions. Those are our boundary lines that our graph can't touch or cross. So we have a vertical asymptote if we cannot cancel out a factor that's in the denominator. And that's written as a line, x equals a number. And again, you can have more than one. Okay, so let's look at a couple of examples. So for each rational function, identify the domain and any vertical asymptotes and or holes. So the first thing that we're going to do, okay, is just like we normally would, I want to factor anything that I can. So in number 1, we're going to factor. So x plus 5, we can't factor. We're going to leave that as is. X squared plus 9x plus 20, we'll factor that to be x plus 5 and x plus 4. Okay, so before I do any type of simplifying, what I want to do is find my domain. So the domain is going to be all real numbers, except x cannot equal whatever our restrictions are. And we can see from here, whatever makes our denominator 0 are the restrictions. So x can't be -5 or -4. So that would be our domain. Okay, then from here, what we want to do is simplify if we can. So we know that we have an x plus 5 on the top and bottom, so those would cancel out. So when we go to write our final answer, remember that when you divide factors that are the same, you really are left with 1. So we have a 1 in the top and an x plus 4 in the bottom. So this would be simplified. We can see that we did cancel out x plus 5s, so that is removable discontinuity. So that means that we would have a hole. Okay, and the hole is going to happen at the value that makes that 0. So we canceled out x plus 5, and we get -5. To find the y value of the hole, we're going to plug in this -5 into the new function. So into this function here. So I'm going to get 1 over -5 plus 4. So this is 1 over -1, which is -1. And notice that the x plus 4, we did not cancel. So that would be a vertical asymptote. And that's going to be written as x equals whatever the value is that makes that 0. And that's -4. So notice that the wholes and the vertical asymptotes are our domain restrictions. Okay, let's look at number 2. Same idea. So first thing again I'm going to do is I'm going to factor. So I will pull out an x here, x plus 2. And then I'm going to factor this to be x minus 9, x plus 2. Okay, so again, first thing I'm going to do is write my domain. So that would be all real numbers except x cannot equal my restrictions, so 9 and negative 2. I want to simplify anything that I can. So x plus 2's can cancel out. So my simplified function is going to be x over x minus 9. I canceled out the x plus 2's, so that's our removable discontinuity. So that's going to be a whole. The x value of the whole is what makes this 0, so negative 2. To find the y, we're going to plug it into the new simplified function. So negative 2 over negative 2 minus 9. So that's going to give us negative 2 over negative 11, which is just positive 2 over 11. And then we did not cancel out the x minus 9 in the bottom, so that would be our vertical asymptote. So x equals 9 would be our vertical asymptote. Okay, and let's look at this last one. So we don't need to factor anything. Remember that x plus 1 quantity squared just means that there's 2 x plus 1's in the bottom. So I'm going to actually just change that to be x plus 1, x plus 1. Okay, so our domain will be all real numbers, except x cannot equal what makes the denominator 0, which is negative 1. Okay, I can cancel out an x. Oops, no I can't. Just kidding. Okay, it's not the same, so I can't cancel anything out. So there are no wholes here, so I'm going to write whole none because nothing was removed. And the thing I did not cancel out in the bottom was x plus 1. So that means I have a vertical asymptote at x equals negative 1. Okay, next we're going to look at horizontal asymptotes. So horizontal asymptotes will at most have one horizontal asymptote. When we focus on the horizontal asymptote, we're going to focus on the degree of the numerator and compare it to the degree of the denominator. So for purposes of explaining, we're going to call m the degree of the numerator, and we're going to call n the degree of the denominator. If m is less than n, the graph has a horizontal asymptote of y equals 0, which is the x-axis. If m is greater than n, the graph has no horizontal asymptote. If m is equal to n, then the graph has a horizontal asymptote of y equals a over b, where a and b are the leading coefficients of the numerator and denominator. Okay? And we can figure out the range. So we already talked about domain. We can figure out the range of a function by looking at the horizontal asymptote. So the range will be all real numbers except for the horizontal asymptote. And again, that horizontal asymptote is that boundary line that our graph is going to not cross or touch. Now the horizontal ones are a little iffy. If it is y equals 0, it can touch it a little bit. Horizontal can be like that. Vertical is a very strict cannot touch asymptote. Okay, so this is something I would write down if I were you guys. Now let's look at these examples here. So for each of these, identify the horizontal asymptote and then identify the range. Okay, so remember with horizontal asymptote, we're checking the degree of the numerator and the degree of the denominator. Okay, your degree is your highest exponent. So in number 1, the highest exponent in the numerator is 1. The highest exponent in the denominator is 1. Okay, they are equal. When they are equal, we take the ratio of the coefficients. So negative 2 is in front of this x, 1 is in front of this x. So the horizontal asymptote would be written as y equals, and it's in this case negative 2, because it's negative 2 divided by 1. So that means our range, the y values that can be part of our function, would be all real numbers, except y cannot equal negative 2, because that's our horizontal asymptote. Okay, number 2, check the degrees. The degree on the top is 1, the degree on the bottom is 2. So the bottom is larger than the top, so that means that the horizontal asymptote would be y equals 0. So that means that our range would be all real numbers, except y cannot equal 0. Okay, and for the last one, again, check your degrees. The degree of the top is 2, the degree of the bottom is 1. Because the top is larger, this means that there is no horizontal asymptote. So there is none. So that means that the range will be all real numbers. Right? There's no restriction on the y value since there is no horizontal asymptote. And then the last key feature that we're going to look at are the intercepts. Okay, there's two different intercepts that we have. We have the x-intercepts and the y-intercept. Okay, x-intercepts, you're going to get these by setting the numerator equal to 0 after we've simplified and solving for x. There can be more than one x-intercept, and we want to make sure that we write them as points. It's going to be the x value, comma 0. For the y-intercept, you're going to plug in 0 for x and solve for y, and you can do this in either the original equation or the simplified. The shortcut is just to look at the constant terms, so that's the terms that don't have an x, and then divide. There can be at most 1, and it should be written as a point, 0, comma, the y value. Okay, so again, I would write these down so you have everything in front of you. So let's look at these examples. Okay, so for each of these, identify the x and y intercepts. So first we're going to do x-intercept. So for the x-intercept, we have to make sure that it's simplified first. So I'm going to go ahead and simplify this. So this is going to be x plus 2 over x minus 9, x plus 2. So it's like one of the ones we had earlier. Those will cancel out. So our new function is x over x minus 9. So for the x-intercept, we're going to take the numerator and set it to 0. So x equals 0. So the point that we're going to write is 0 for the x, because that's what we solved for, and the y value for an x-intercept will always be 0. So it's going to be some number, comma 0. And in this case, it was 0 to start as well. For the y-intercept, okay, we can use the simplified one here. You can do one of two things. You can plug in 0 for x, so we get 0 over negative 9, which is just going to give us 0. So the x will always be 0, the y will be whatever we solved for, and in this case it was 0 again. The shortcut is to look for the constant terms. Because there's no constant term in the top, we know that it's going to be 0. Okay, this might make a little more sense in the next one. So in number 2 here, again, we know that this one is x plus 1 in the bottom. Nothing is going to cancel out. So for the x-intercept, we're going to take the numerator. Because it didn't simplify, we'll just use the original. And we're going to set x minus 1 equal to 0. So when I set x minus 1 equal to 0, I'm going to get that x is equal to 1. Remember that the y value will always be 0 for the x-intercept. Okay, so 1, 0. For the y-intercept, okay, we're going to plug in 0 for x. So our x will always be 0 in this case. If I plug in 0, 0 minus 1 is negative 1. 0 plus 1 is 1. Squared is 1. So we get negative 1 over 1 or negative 1. If we were doing this the shortcut way, the constant term on the top is negative 1. The constant term on the bottom, if this was in standard form, would also be a 1. And we can just divide negative 1 and 1 to get negative 1. Okay, and let's look at this last example. So again, we want to make sure that we factor everything first. So here we're going to have x minus 5 and x minus 4 over x plus 2, x plus 2. Okay, here nothing cancels out. So for the x-intercept, we're going to take the numerator and set it to 0. But there's two factors, and that's fine. We can have more than one x-intercept. So we're going to set x minus 5 to 0. So we're going to get 5. Remember that y will always be 0. And then we're going to take x minus 4 and set it to 0. So we get 4. And remember that the y will be 0. For the y-intercept, we again can plug in 0 for x. So we can either plug it into the simplified one or the original. So the original might be a little bit easier. If you plug in 0 for x, right, all of these are going to be 0. So that's why we say that the shortcut is to look at just the constant terms. So 20 over 4 is going to give us 5. So remember that the x value of a y-intercept will always be 0. And then 20 divided by 4, we said was 5. So our y-intercept would be 0, 5. Okay. So you guys are going to try these 4 problems. Okay, you want to make sure that for each of these problems, we identify everything that we talked about. So you're going to find the domain, the range, the vertical asymptotes, the holes, the horizontal asymptote, the x-intercepts, and the y-intercepts.